Let's discuss the most common types of forces, the ones that appear most often on our free body diagrams. They're contact forces, gravity, tension, and drag. We'll look at each of them. And then at the end, I'll ask you to try drawing a few free body diagrams. Okay, number one, contact forces. This represents an interaction between solid bodies or between two solid surfaces or between a solid body and a solid surface when they come in contact with each other or touch each other. When two solid bodies come in contact, we sometimes prefer the term an applied force. So F sub C for a contact force, or often we'll say F sub A for an applied force. We call it an applied force most often when it's a person or an animal or a machine actively pushing or pulling on an object. Now, contact with a surface. The contact force exerted on an object by a surface is usually modeled as if it were two separate interactions. It's usually convenient to break the contact force apart into two components, which are treated as if they are two distinct forces. The component of the contact force that is perpendicular to the surface, that's called the normal force, F sub capital N, or sometimes just a capital N to represent that component of the contact force that we call the normal force. The other component of the contact force, the part that's parallel to the surface, that's what we more commonly know as friction, the force of friction, F subscript little f. So here we've got a few training stones feeling contact forces with this surface that they are in contact with. This one is at rest on this slope. This one is sliding to the right sliding to the left. And this stone here is being pressed against the wall by Yoda. So in each case, we've got a contact force, Fc, with the surface. That's a force on the stone due to the surface. But normally in our free body diagrams, we don't draw these contact forces like this. We break them into components. And I've kind of drawn dotted rectangles to indicate the legs of the right triangles. That would be those components. So on your free body diagrams, you would actually draw something like this. Here, for the stone sitting on the surface, the component of the contact force parallel to the surface, that's friction. Friction pushing upwards, keeping the stone from sliding down the surface right there. And then here's your normal force coming out perpendicular to the surface. Not straight up, because our surface isn't flat. Our surface is tilted, so our normal force comes out perpendicular to the surface. Here, for the sliding stone, its velocity is to the left. Friction, of course, will be pushing to the right. Friction opposing that sliding. That is parallel to the surface. There's our force of friction, the parallel component. And then here's our perpendicular component, the normal force pointing straight up perpendicular to the surface. For the stone being pressed against the wall, the normal force here, this component, is pointing straight out to the left, perpendicular to the surface. This normal force is tilted all the way 90 degrees. And here friction is pointing straight up. It's friction holding the block against the wall, opposing gravity. That's, of course, pulling the block down. So these are the two components of the force the wall is exerting on the stone. That covers contact forces. Let's talk briefly about the force of gravity as it appears on our free body diagrams. It's a long-range, non-contact interaction between any two objects. Every atom in the universe attracts every other atom in the universe with a weak gravitational pull. Only an enormous lump of matter, like a whole planet, exerts a strong enough gravitational pull to be noticeable in everyday life. If we're near the Earth, then the force of gravity exerted on an object by the Earth has these two characteristics. It always points toward the center of the Earth, and its magnitude, its strength, is proportional to the mass of the object. So more massive objects feel stronger forces of gravity. Here I've got a few of these space penguins flying and jumping about, and we see a force of gravity on each one of them. Note that if they're all about the same mass, then their forces of gravity are all about the same magnitude, and they're all pointing straight down, and they are constant no matter what these little fellows are doing, no matter how they're moving, the force of gravity always points straight down. It's like a constant that doesn't change no matter how the object moves. Here I've got a stone of mass m and a larger stone of twice the mass, so this stone would feel twice the force of gravity that this one does. One more note on forces of gravity. Let's say that we're looking at larger objects now, maybe in space. Any two objects, mass A and mass B, they exert gravitational forces on each other, equal and opposite gravitational forces, in fact. The strength or magnitude of the gravitational force is proportional to the product of the masses. You multiply the masses together to find out how big the force of gravity between them is going to be. The force of gravity exerted on mass A by mass B acts at the center of mass A and points toward the center of mass B. In this example, I've got three masses, a star, a planet, and a moon here. Their centers are all about the same distance apart, but they are three very different masses. And for the star and the planet, these are the gravitational forces they exert on each other. This is the force on the planet due to the star. This is the force here on the star due to the planet. Note they're equal and opposite. If we look at the forces between the star and the moon, here are those pair. They are also equal and opposite, but note they're smaller in magnitude because the star's mass times the moon's mass is a smaller number than the star's mass times the planet's mass. Likewise here, the moon and the planet also pull on each other with a pair of equal and opposite forces right here, but those are even smaller in magnitude because the moon's mass times the planet's mass is smaller than any other of the products here. Okay, that's force of gravity. Let's look at forces of tension. A force of tension we usually indicate with a F sub capital T, or sometimes just a capital T to indicate a force of tension. And that term tension can mean two similar things. Tension is a concept used when modeling interactions with ropes, strings, wires, cables, chains, elastic bands, or any other such object that's used for pulling, or any solid body such as a rod or a beam that is being pulled or pulling from either end. So one thing that a force of tension can mean is a contact force exerted on an object by a rope or a rod or one of those other types of things I mentioned. That's attached to and pulling on the object. Tension is always a pulling sort of force. And that tension always points along or parallel to the rope that's doing the pulling away from the object. So if this stone here is being held in static equilibrium, hanging there at rest, supported by these two vines right here, then there would be one force of tension from this vine, one force of tension from that vine. This stone over here that's swinging like a pendulum, the force of tension on it points along the rope, away from the stone. And note that as the stone moves, the force of tension moves as well to stay parallel to the rope. So the force of tension changes direction as the vine here shifts. The other meaning of tension is to represent an internal interaction inside the rope itself or inside this vine here. Internal interaction between parts of a solid stretched out rope or a rod. And here the force of tension is still parallel to the rod itself. If we zoom in on our vine and look at this little vine segment right here, this little section right in the middle, that section is being pulled by the part of the vine above it. The upper part of the vine is pulling upward on this little segment. The lower part of the vine is pulling downward on this little segment, and we would call those forces of tension also. If the vine's at rest, then this segment feels equal and opposite forces of tension from above and below, canceling out. That's tension internally within the vine or the rope itself. Last topic is drag force. Drag force. F sub lower script with a subscript with a little d right here. A drag force, that's an interaction between a solid body and some fluid medium. Fluid can mean a liquid or a gas. So typically this is air or water. Drag forces are similar to friction in that they always oppose relative motion. the medium attempts to match the velocity of the object to the velocity of the medium. And there are two possibilities here. One is that you've got objects moving through a medium that is still. So here, these little penguins leaping off experience a drag force as they move through the air here. And that drag force has two properties. One, it's at every instant, it's exactly opposite your velocity. So if its velocity is this way, then at that moment, drag force is exactly opposite the velocity, always opposing velocity. And then as this fellow speeds up and his velocity tilts, the drag force tilts with it to stay exactly opposite the velocity. As the velocity, as the speed becomes greater, then the magnitude of the drag force becomes greater as well. So that's a solid object moving through a still medium. The other possibility is that the medium is moving. Your fluid medium could be moving relative to the object. So here we've got this raft with a sail. That's the object we're considering. And we've got a wind moving at a greater speed than the raft is. So you would feel the wind blowing. That's because the air is moving at a speed greater than your speed. And that wind hitting the sail here, that's going to exert a drag force on the sail. So my point here is that what we would call a drag force isn't slowing this raft down, it's actually speeding it up. When you feel the wind pushing on you, that's a drag force that can speed you up. The wind is trying to match your speed to its own speed. Here the wind is trying to match the speed of the raft to the wind speed. So we get a big force to the right. At the same time, this raft is moving through water here, a river in which there is a current to the left. So that current colliding with the underside of the raft is also going to exert a drag force on the raft, trying to get the raft to match the velocity of the current. So there's going to be a drag force due to the water here on our raft as well. So these two different drag forces, in this scenario, I've indicated that our drag from the wind is greater than the drag from the current. This drag is trying to speed the raft up. This drag is trying to slow the raft down. We can see that the winner here, the net force, is going to be to the right. The wind is going to exert greater drag force than the water. So our raft and its passengers will be accelerating to the right, speeding up thanks to drag. Okay, that's the three types. Now I want to look back and ask you to draw some free body diagrams for 3 of these stones that were hidden in our scenario. Let's go back to this stone right here that's being pressed against the wall, held at rest against the wall. Draw a free body diagram for this stone at this moment. That's number 1. 2 more I want to do. The second stone I want you to draw a free body diagram for is this one that is sitting here at rest, suspended by these 2 vines. And I want you to think carefully here about the magnitude of these 2 forces of tension. You can see that I've drawn this tension, with a smaller magnitude than this one. Why did I do that? Can you explain it? Can you draw the rest of the free body diagram and figure out why these tensions have the magnitudes that they do? Okay, that's FBD number 2 that I want you to do. The third stone I want you to draw a free body diagram for is this one that's sitting on the raft. It's at rest with respect to the raft, so just sitting on the raft, but it is accelerating with the raft to the right. Stone's accelerating with the raft to the right. And can you draw the free body diagram for the stone that indicates that acceleration? What's causing that stone to accelerate? You can ignore the wind on the stone, but take account of all other forces. Okay, pause the video and draw those 3 free body diagrams for those 3 stones. Okay, ready for the results? This stone's FBD should look like this. We've got gravity pulling straight down, being opposed by the force of friction with the surface straight up. Those are equal and opposite. And then here's the applied force from Yoda pushing to the right. That's being opposed by the normal force from the surface pushing to the left. And that pair is equal and opposite. So all the forces have canceled out, and our stone here is in static equilibrium. for the hanging stone. This FBD looks like this. 3 forces on it, the 2 tensions, and then of course the force of gravity pulling straight down. Now the lengths of these represent the cancellation of the horizontal components of the forces and the vertical components of the forces. So the component of this tension pulling left, that x component right there, has to exactly be canceling the x component of this force pulling to the right. So that the net force horizontally is 0. So those 2 legs of these 2 triangles should be equal in size. Then vertically, this tension has a vertical component pulling up, this one has a component pulling up. This upward component plus this upward component should be equal in magnitude to this downward component. So this plus this should have sizes add up to that right there for an accurate diagram. Lastly, the one at rest, or sitting on the raft here, but accelerating with the raft. What is accelerating this stone to the right? It is friction, of course. Friction between the stone and the raft surface that it's sitting on. Friction is pushing the stone to the right, preventing the stone from slipping off the rear of the raft as the raft accelerates forward. Remember that friction always opposes slippage. So the friction, kind of like a traction here, is going to grab onto that stone and push it forward, trying to keep it with the raft so it doesn't slide off the back. Meanwhile, the normal force from the raft surface is exactly balancing the force of gravity downward on that stone.